Okay, let others also join and we'll start in about a few minutes. All right, let us start then. Yes. So, very good evening, everyone. My name is Varnit Kapoor, and I'll be taking up the tutorial for week 4 on thermodynamics. And I hope you all are regular with your lecture videos as uploaded on Nptel, as well as the tutorial videos who all have missed can watch out on the YouTube as well, all the recording sessions. Okay. All right, let me just share my screen so that we can start the session. My screen is visible. Let me see one second. Okay, yes, now it's visible. So in the last tutorial, we started with first law of thermodynamics, okay? And the last topic in that was we were discussing about the important points regarding heat and work. Okay? What is a triple point? It's a point on the curve, PT curve, surface on PV curve, PVT curve, okay, and the triangle on a UV curve and so on. So I hope you all are regular with this. So today we'll start with steady flow energy equations. Okay, let me write it. Steady flow energy equations. In short form, SFE. SFE. All right. So what is basically a steady flow energy equation? It's basically nothing but an equation that describes the conservation of energy in a flowing system. Okay, describes the conservation of energy in a flowing system. So it is used for open system works. You know very well that what is open system, what is closed system work. We have very well discussed in detail in our previous tutorials. Working under steady conditions. That steady means that doesn't change with respect to time. Okay, that is where the rate of mass flow and the energy flow are constant with respect to time. So that means the property does not vary with respect to time. Whatever the mass is at entry and exit will be same. Okay. So let me write. It is an equation that describes the conservation of energy in a flowing system. Okay. It is for open system. Then steady flow means that property doesn't vary with respect to time. Means that property doesn't vary with respect to time. So short form for with respect from now onwards, I'll write WRT. Okay. Which means, sorry, I'll write with respect is WRT to time. Okay. Which means mass at entry, mass at entry and exit of the control volume are same. So we know that what is a control volume. We discussed very well in our previous tutorial as well. Okay. What's a control volume? What's a control mass, control surface? Okay. So let me write the nomenclature for the things which I'm gonna use here. So here H is basically specific enthalpy. Okay. Then U is specific internal energy. Then KE is specific kinetic energy. Okay. So write K also in short, small case. All right. And PE is specific potential energy. Okay. So what is specific potential energy? MGH. Specific means with respect to mass. That means we are converting it into a intensive property independent of the mass. Okay. Then we have PV, which is nothing but flow work. We discuss what is the meaning of flow work in enthalpy discussions. Z is the datum head. Then Q is your heat interaction in the system. and W, sorry, is your work interaction. M dot is your mass flow rate, and remaining C1, comma C2 are your velocities. Okay, into and out from the system. All right, and 1 and 2 is the subscript which we will use at inlet and outlet section. Okay, so I'll make a control volume for you. So we have a control volume like this, which has an inlet this. Okay, this whole system is at a has some datum, suppose here. Okay, so this is your datum, right? The inlet is, this is your inlet. To the control volume. So this is your control volume. And this is your outlet. So inlet is at some distance. At a datum head of Z1, and outlet is at a distance, datum head of Z2. Okay. Right. Okay. So whatever mass flows into the system is mass extracted out of the system. These all things are the inlet are all the properties. H1, kinetic energy 1, potential energy 1. Okay. Then your specific internal energy, all of these are in specific terms, specific kinetic energy, whatever I've wrote here in the nomenclature. Okay. Then flow work at the inlet and speed at the inlet, C1. Same goes for the outlet as well. So H2, kinetic energy at outlet, potential energy at outlet, internal energy at outlet, flow work at outlet, and speed at outlet. Okay. There's a heat interaction with the system. All right. And there's a work interaction with the system. Okay. So this is the whole setup. And now we are going to apply. Also, one thing I missed here. So whatever mass flow rate is here is the same mass flow rate here. Okay, both the mass flow rates are same, M and M. That's why I hadn't written M1, M2 kind of thing. Okay. So as the definition, as per the definition, it says that describe the conservation of energy in the flowing system. So this is your flowing system. So some fluid is entered through the inlet into the control volume, and it has flown out of that control volume from the outlet. Okay. So the energy at the inlet is equal to the energy at the outlet. That is the thing. So what is the energy at inlet? If I write U1 internal energy plus flow work, okay, plus kinetic energy plus potential energy at the inlet plus the heat interaction. So if you supply some heat to the system, now what is the energy at the outlet? Okay, so this is inlet. and this is outlet. Same. Internal energy at outlet, flow work at outlet, kinetic energy at outlet, potential energy at outlet, plus work. Okay, whatever work you have received from the system. We know that by the definition of enthalpy, this is specific enthalpy is sum of specific internal energy plus flow work. This was the definition which we discussed in the previous tutorial. Similarly, this is a specific enthalpy at outlet. Okay, so what you can write U plus PV as H. Okay, now if you see the enthalpy has a unit of kilojoule per kg Kelvin. Okay, whereas your kinetic energy has a velocity in the form of meters per second. Meters per second. You wanted it to terms of in the terms of the energy head to be in terms of kilojoule per kg only. So enthalpy has a unit of, let me write what I'm trying to say. This has a unit of kilojoule per kg Kelvin, and temperature also Kelvin, Kelvin cancel. So enthalpy has a unit of kilojoule per kg. Okay. Whereas kinetic energy has a unit in terms of has a velocity which is in terms of meters per second. So meter square per second square. You want it to the terms of kilojoule per kg only. So you'll divide it by 1000. Okay. So I'll write step by step here. So this is H1 plus kinetic energy 1, potential energy at 1 is equal to H2 plus kinetic energy at 2 plus potential energy at 2 plus work done. This whole unit need to be in terms of kilojoule per kg, all the heads. So kinetic energy is half V square, specific kinetic energy. It's not half mv square. We are writing specific with respect to mass. Okay. So half mv square is your kinetic energy. If you divide by m, so that is specific kinetic energy, half v square. But it is in terms of not in terms of kilojoule per kg. You want it in terms of kilojoule per kg. So you'll divide by 1000. Okay. So that is half v 1 by 2000 v square. That is what I'm trying to say. So I'll write h1 plus 1 by 2000 c1 square, velocity at inlet. Similarly for the head of potential energy as well, gz1 by 1000. Again, z is in meter, g is in meter per second square. You want to convert it in kilojoule per kg. So divide by 1000. So z1 is the head. Oh, I wrote this z1 plus heat interaction. Similarly at outlet, h2 plus 1 by 2000 speed at outlet, c2 square plus g z2 by 1000 plus work done. So all of this has a unit of kilojoule per kg. Okay, this is your unit of this, all the heads in the all the energies. Okay. I'll write that also here. I'll write that in the form of note. That is what I'm trying to say. Kinetic energy is half mv square or c square, whatever you want to write. So kinetic energy, this is kinetic, not specific kinetic energy. So kinetic energy has a unit of joules. And this has a unit of mass is for kg and speed is for meter square per second square. All right. So if you take this, transpose it this side, so that will be joule per kg is equal to meter square per second square. But we want the unit in terms of kilojoule. So that's why to make it kilojoule, we'll divide by 1000. So it's kilojoule and it's 1000. All right. You got it now. I hope clarification is there. Okay. Yes. Now, this was the energy in terms of the specific terms. If I want in terms of the complete energies, okay, not specific energies. So I'll multiply with the mass flow rate. What is the mass flow rate at inlet and outlet? But it is same at inlet and outlet. So I'll multiply mass flow rate with inlet H1 plus C1 square by 2000 plus GZ1 by 1000 plus. So heat interaction already had, okay, the Q dot, okay. M into Q is Q dot. So if you see, there it was written Q only. So if I multiply M dot with Q, I'm just writing it as Q dot, okay. So Q dot, heat flow rate. And at outlet, also mass flow rate is same. So M dot H2 plus C2 square by 2000 plus GZ2 by 1000 plus same work W dot if you multiply with it. So now it has a unit of kilojoule per kg. This has a unit of kilojoule per kg. Oh, sorry, both kilojoule. Kilojoule per kg. And this has a unit of kg per second. So kg cancels. It is kilojoule per second. And kilojoule per second is nothing but kilowatt. That is kilowatt. Okay, this is your unit. So if your examiner asks you the question is in the units are in watt, then you have to multiply your watt or kilowatt, whatever. Then you have to multiply your above equation, the steady flow energy equation, with mass flow rate. If it is in terms of kilojoule per kg only, okay, no watt is there. So it's fair enough to use the above equation. Okay. All right. This is the whole concept of steady flow energy equation. Both of these are very important. Very important. Similarly, this equation as well. All right. Now let us come to some special cases of the devices. Okay. All these devices are open system devices, but in a cycle they behave as a closed system. This term we have understood very well in deep in our first tutorial. Okay. So special cases. Okay. So first cases of nozzle. What is a nozzle? A nozzle is nothing but a mechanical device of variable cross section which is used to increase the kinetic energy at expense of pressure energy. So whatever pressure energy you apply at the inlet, because a nozzle has a varying cross section, okay, either it's a diverging to converging or converging to diverging. Okay, so a nozzle is nothing but a mechanical device which has a variable cross section. So whatever pressure energy you apply, it is converted into a kinetic energy, okay, which increase the kinetic energy of the system. Okay, so it is a mechanical device of variable cross section which is used to increase kinetic energy at expense of pressure energy. Okay, so suppose you have a device like this. So whatever the pressure energy is here, it is converted into a kinetic energy. Okay, it's not a, it's a very general way of saying a device is like this. Okay, that with the converging cross section. It is not always true. When you'll deal with compressible flows, you'll understand that why. Okay, so we'll use the steady flow energy equation using SFEE. The SFE says that H1 plus, right, in terms of kinetic energy only, potential energy plus Q is equal to H2 plus kinetic energy at 2 plus potential energy at 2 plus work. All right. So we'll assume that we'll make some assumptions for the nozzle is that we'll not take the potential energy changes. We assume that our device is from the datum. If you, this is your datum, this is your nozzle. So both inlet and outlet are at same datum. Okay, Z1, Z2 both are at same level. Okay. Next thing, it is well insulated. So no heat interaction takes place and no work interaction also take place. Okay, from the nozzle, we don't obtain some work out of it. Okay, and as the energy kinetic energy increases, so that means your outlet velocity C2 will be very high compared to C1. Okay, so you can neglect the kinetic energy at the inlet. So all these are assumptions. What are your assumptions here? So the first is neglecting potential energy changes. Second is well insulated. Third is no work interaction. And fourth is your C2 is much greater than C1. So neglecting inlet kinetic energy. Okay. Neglecting inlet kinetic energy. Now use all these assumptions and put it into the steady flow energy equation. After putting all these assumptions in steady flow energy equations, what you will get that enthalpy is only remaining at the inlet. This has been gone to 0. This is also 0. And there is well insulation is there. So this is also 0. So you're left with only H1 at the inlet. Whereas at the outlet, again kinetic energy will be there. C2 is very high. Then potential energy is 0 and no work interaction is there. So final equation will be H1 is equal to H2 plus kinetic energy at 2, specific kinetic energy. Okay. So specific kinetic energy can be written as H1 minus H2. All right. So it is 1 by 2000 C2 square is equal to H1 minus H2. So C2 comes out to be 44.72 of under root of H1 minus H2 because under root of 2000 is 44.72 only. Okay. So this is your final speed which you got for the nozzle. Okay. Now let's come to the next device, that is diffuser. So what's a diffuser? It's a device again of a variable cross section which is used to decrease the velocity or kinetic energy with increase in pressure energy. Just opposite of nozzle. Okay. Mechanical device of variable cross section used to decrease kinetic energy with increase in pressure energy. Okay. If you follow the same assumptions as above, okay, on following same above assumptions as of nozzle. So now you using SFEE. What will you get? Again, H1 will be there. This time, kinetic energy at inlet is high, is equal to H2. Okay. All the other things are 0 this time. So from here, C1 will be 44.72 under root of H2 minus H1. Okay. The same, just the difference of enthalpy is difference. Earlier it was H1 minus H2. This time it is H2 minus H1. But for a general purpose, you have to remember that under root of anything shouldn't be negative. Otherwise, it will become imaginary. So whenever you are doing a calculation for numerical purpose, then you should always remember that under root should be a positive value. So you won't be making any mistakes. Anyways, now coming to the next device, that is turbine. Third. So what's a turbine? So it is basically a work producing device in which energy is transferred from the working fluid to the rotor. So that is, work is done by the system because we want work from the system. That's why we have made a turbine. So in case of turbine, expansion of the working fluid takes place, which results in decrease in the pressure. Okay. I like that. It is work producing device in which energy is transferred from working fluid okay, to motor, to rotor. That is, work is done by the system. So working fluid, the energy is transferred from working fluid to the rotor and we extract the work out of the system. So in case of turbine, expansion of working fluid takes place, which results in decrease in pressure. Okay. So water or your working fluid is if it's a steam turbine, so steam is your working fluid. Okay. So device looks like something. Okay. So this is your insulator. So this is your turbine. This is your inlet. So in the power plant subject, you will be dealing with more details of the formation of the turbine, the blades, and so on. Okay. And this is your outlet. Okay. Now again, we'll make some assumptions. So what are the assumptions here? Before applying SFE. So first assumption is, again, you will neglect the kinetic energy changes. So whatever the speed is at the inlet of the turbine, it's same as the outlet of the turbine. So neglecting kinetic energies. Second, you neglect again the potential energy. So your turbine is at same head. Okay. All right. So so don't go with this diagram like this. Don't understand that this is inlet, so this is Z1 and this is outlet, this is Z2. Please don't get confused. The diagram is like that, but your whole turbine is at same level. This is just for the reference drawing purpose. So neglecting potential energy changes. But there can be instances where the inlet outlet are at different positions, but we are taking the assumptions that they are at same datum. So potential energy changes will be also neglected. And again, it is well insulated, so no heat interaction. Assumed to be well insulated. Okay. So if you use the SFEE here, so again, all the things at the inlet goes to zero apart from enthalpy, because heat interaction, kinetic and potential heads all are zero. At outlet, kinetic potential heads are zero, but enthalpy is there as well as work extracted. Okay, so what is work extracted? It is H1 minus H2. So working fluid has energy more at the inlet. Okay, that is H1, and less at the outlet. That's why it is H1 minus H2. But if you reverse this, H2 minus H1, that will be a pump. Okay. So turbine is a work producing device, whereas a pump is a work absorbing device. All right. So this is your work output from the turbine. Now let's come to pump and the compressors. Pump. So this was third. Now is the fourth device. Pump and compressor. All right. So both are again work absorbing device. Turbine was a work producing device, but pump and compressor both are work absorbing device in which energy is transferred from rotor to the working fluid. Okay, so in your home, if you have a motor, what you do? You take the water from the ground and you pump it to your tank above the household. Okay, so working fluid is getting the energy so from the rotor. Okay, so energy is transferred from the rotor to the working fluid by increasing the potential head. So pump is generally used to handle liquids and is used to increase the pressure of the working fluid. Only the pressure. Whereas compressor is used to increase the pressure as well as temperature. So in the pump, if you switch on the motor at your home, whatever the temperature is at the inlet of the pump and in the tank which you stored at the outlet, both have same temperature. Okay, it's not like that you switched on the pump, it got heated, water got heated. Okay, but in the compressor, it's the scenario different. Here, pressure as well as temperature will also increase. So in the cases of a compressor, if you have in your refrigerator, okay, or your air conditions, so from the evaporator, the cold fluid is entered into the compressor, and after the compression, the hotter fluid comes out of it. So it is used to handle the gaseous phase of the working fluid, the compressor. Okay. So write the things. Both are work absorbing device in which energy is transferred from rotor to working fluid So pump is generally used to handle liquids and is used to increase pressure. Of working fluid. Whereas compressor is used to increase both pressure and temperature. And is used to handle gaseous phase of working fluid. All right. So diagram for a pump or compressor looks like this. So again, same. So this time, this is your inlet. This is your outlet. So arrows and the directions have changed. And again, it's insulated using all the same above assumptions. Okay. Use above assumptions of turbine. Your SFE is H1 is equal to H2 plus work. Okay. But what will work this time? The work is not on the right hand side because work is absorbed. So this time work will be on the left hand side. So that is plus work is equal to H2. Okay. It is at the inlet. So work is H2 minus H1 because I have written the first thing. It's a work absorbing device. Work absorbing device. Okay. Now coming to boiler and evaporator. The next device is fifth device. So again, it's a mechanical device in which heat is absorbed at constant pressure by the working fluid. And both are heat exchangers only. The evaporator and boiler both are heat exchangers. Okay. It's a mechanical device in which heat is absorbed at constant pressure by working fluid. Both are heat exchanger, which exchange the heat. So again, you will make some assumptions here. That kinetic energy change is 0, potential energy change is 0. Okay, and work is 0 because from boiler or evaporator we don't extract work, only the heat change is there. Okay, so the first assumption is change in kinetic energy is 0, change in potential energy is 0, and work is 0. I'm writing in the short form. Okay, so using SFE now, so there is enthalpy at the inlet as well as heat interaction and enthalpy at the outlet. Rest all the things are 0. So heat interaction is H2 minus H1. Okay. So heat absorbed by the system. So temperature increases. Okay. If it is 2 minus 1, then heat is absorbed by the system. Next device is condenser. So sixth device. So what's a condenser? It's again a type of heat exchanger in which heat is rejected by the working fluid at constant pressure. Heat is rejected by boiler and evaporator, both absorbs the heat. Okay, so evaporator is in the your air conditions, so you absorb the heat of the room, okay, in the evaporator, whereas the condenser rejects the heat out of the system. So the AC unit, if it's a split AC in your homes, so the outdoor unit is a condenser which takes out the heat out of the system. Okay, some fin arrangement is there. And boiler is used in the turbines, okay, which condenses out, which absorbs the heat. Okay, so condenser is a type of heat exchanger in which heat is rejected by working fluid at constant pressure. Okay, again, it will be just reversed using the above assumptions. So using SFEE, you will get Q is equal to H1 minus H2. Okay, so heat at inlet is higher compared to outlet. All right. Next is a throttling device. We'll see again the throttling device in your refrigerators. Okay, throttling device. So it's a flow through a restricted passage. Okay, particularly an open valve is there or a porous plug is there, which is known as a throttling device. Okay. Flow through a restricted passage. Or you can say partially open valve. Or you can say a porous plug. Or somewhat like the geometry, etc., is known as throttling. This is a process, throttling. Okay. Again, some assumptions here. So what are the assumptions? Change in kinetic energy 0, potential heat is 0, work done is 0, and it's adiabatic. So again, your heat exchange is also 0. First, change in kinetic energy, 0. Change in potential energy, 0. There is no work extracted out of the throttling device, as well as there is no heat exchange, adiabatic process. So using SFEE now, so all the terms are going to be 0 except for enthalpies. So H1 is equal to H2. So enthalpy remains constant in the throttling process. The throttling is also known as constant enthalpic process or isenthalpic process. As well as throttling result in decrease in the pressure because of the expansion which happens, and it is a irreversible adiabatic process. Adiabatic is there, and it's as well as irreversible. You cannot take. It's not going to follow the same path. Okay, when you take the system back, try to take the back to the original state. Okay, so I'll note the point down in the form of note. Throttling is also known as constant enthalpy. Or isenthalpic process. Next point, results in decrease in pressure. This you will understand very well in your refrigeration concepts, refrigeration, air conditioning subject. Okay. Throttling results in decrease, where you will understand the VCRS cycle. Throttling process is there, which is a constant enthalpy process. Okay, expansion of the fluid happens there. Okay. So I'll give a glimpse like this. This is a cycle, what look like. So from 1, 2, 3, 4. This process from 3 to 4 is a throttling process where volume is expanding. This is a PV plot. Okay. So expansion of volume happens from 3 to 4. Okay. Just for your reference, I'm saying. Decrease in pressure during expansion. And it's a irreversible adiabatic process. All right. Just give me a minute, guys. Okay, we're back. Now let's come to the concept of free expansion or unrestrained expansion. How do you say unrestrained? So what is a free expansion? It's basically an expansion in a vacuum is known as free expansion of the system, or without expansion without any restriction if you don't provide any kind of restriction to the system. So it's an irreversible process in case of, and in this case of free expansion, your heat change, work change, energy change, internal energy change, all are, you can say, are zero. Okay, suppose you have a chamber. So you have a chamber and it is separated by two partitions. One has gas, one is vacuum. If you open the partition, the whole chamber will fill with gas. Okay, it's an insulated chamber. So as soon as you open the partition, so it's a free expansion against the vacuum of the gas. I'll make a diagram here. So you have an insulated chamber. So it's partitioned with, there's a wall here. So the left partition has a gas and right has a vacuum. As soon as you open this valve, what happens? Okay, as soon as you open this valve, this insulated chamber is completely filled with gas. Okay, so this happens in the free expansion. Okay, against the vacuum. Gas is expanding against the vacuum. So it's an expansion. Against vacuum. Is known as free expansion or expansion without any restriction. It is irreversible process. And in case of free expansion, values of change in heat, change in work, change in energy, or change in internal energy all are equal to zero. Okay, all of them are zero. Also, if it is a ideal gas, if the gas is ideal gas, then DH enthalpy change will also be zero. Okay, because enthalpy is a function of temperature for the ideal gas. It is, then DH is also zero. All right. Now there can be one important point you can ask. Is that an important question raises here? If du is zero, change in internal energy is zero. You know that we write in the form of note. What I'm trying to say, if du is zero, all right, that means u2 minus u1 is equal to zero. Internal energy at final position and initial position is zero. That means u2 is equal to u1. Okay. And we know that for an ideal gas, internal energy is a function of temperature. For ideal gas, U is function of temperature. Okay, so can we say that? So T2 is equal to T1, CVT, MCVT2 is equal to MCVT1. So T2 is equal to T1. But does it mean that it's an isothermal process? Free expansion is an isothermal process. Can we say that? Can we say that free expansion is an isothermal process? And if we say that, then we are violating our statement that isothermal is a reversible process. But free expansion is an irreversible process. So it's a contradictory thing happening here. Isothermal process is a reversible process, but free expansion is an irreversible process. But this statement, this conclusion gives us that it is showing that it can be an isothermal process. That final temperature and initial temperature are same. So the answer for this is no, we cannot say that free expansion is an isothermal process. Although mathematically temperatures are coming out to same, but what is the inference from here is that why they are coming same. Due to the expansion of the gas, the temperature decreases. But as the molecule expands due to the expansion, due to friction between those molecules, the temperature again increases back. So temperature adjusts itself in such a way that initial temperature and final temperature are same. It is not that it's an isothermal process. Okay? So it doesn't mean, I'll write, then you'll understand more. So it doesn't mean it is isothermal process, since isothermal is process is reversible. Okay, process, but free expansion is irreversible process. Once the throttle has been opened, this valve has been opened, the gas has filled the complete. You cannot change back into create a separate vacuum and gas again in that chamber. Okay, expansion is free expansion is irreversible process. Because due to expansion, initially temperature decreases, temperature drop downs, but as molecules expand, due to friction between them, that is the viscosity. Viscosity is the friction in the gas or liquid molecules. Between molecules, temperature again rise back. Okay, so therefore temperature adjusts itself such that final temperature and initial temperature are coming out to be same. Okay, all right. I guess you understood the concept of free expansion. Now I'll give a question to solve. Okay, it's the first question we are going to solve after learning all these concepts. So the question states that air at temperature of 15 degrees Celsius passes through heat exchanger at velocity of 35 meters per second, where temperature is raised to 850 degrees Celsius. It then enters the turbine with same velocity of 35 meters per second and expands until temperature falls to 600 degrees Celsius. On leaving the turbine, air is taken at velocity of 65 meters per second to a nozzle where it expands until temperature has fallen to 450 degrees Celsius. If air is flowing at a rate of 3 kgs per second, then you need to calculate first rate of heat transfer to air in heat exchanger. Second, power output transfer to air, power output from turbine, assuming no heat loss in turbine. Third, velocity at exit from nozzle, assuming no heat loss in nozzle. Assuming no heat loss in nozzle. Okay. Pretty simple question. You have to use SFE. So zoom out. Yes. So take few minutes, solve it, then we'll get back to the solution. I'll also solve it for you. Okay. Okay, I guess every one of you have solved. I see the answers in the chat box. Great. All right. So let's start solving this. So let's come to the solution. So we have a setup where we have a heat exchanger, we have a turbine, we have a nozzle. Okay. Let's first make this flow diagram of it. So we have an heat exchanger, then we have a turbine, and then we have a nozzle. Okay, nozzle. Okay, so this is our system looks like. So this state is state 1. Sorry. This is state 2. This is state 3. So this is our flow is going. So air first passes through the heat exchanger at a velocity of 30 meters per second. So C1 is 30 meters per second. Then where temperature is raised to 800 degrees Celsius. So not 800, it's 850, I guess. Yeah. From 15 degrees Celsius. So at T2, temperature is 850 degrees Celsius and speed remains same. What is speed? 35. Okay. 35 meter per second. Okay. And speed remains same. So C2 is again 35 meters per second and temperature has rise to 850 degrees Celsius. Okay. It enters the turbine with same velocity, 35 meters per second. That is at C2 expands until temperature falls to 600 degrees Celsius. So CT3 here, 600 degrees Celsius given to us. On leaving the turbine, air is taken at a velocity of 65 meters per second. Okay. So I'll write first C3, 65 meters per second. And T3 is how much? 600 degrees Celsius. All right. Where it expand, then it is taken at a 65 meters per second to a nozzle where it expand until a temperature has fallen to 450 degrees Celsius. Okay. And so temperature at position 4th is how much? 450 degrees Celsius. All right. Mass flow rate is given as 3 kgs per second every time. Mass flow rate 3 kg per second at every instance. Okay. And they has asked rate of heat transfer, power output, and velocity at exit. Correct. Velocity C3 or C4 is unknown. They have asked. First part, let us do. That is rate of heat exchanger to air in rate of heat transfer to air in the heat exchanger. Use SFE, simple, between 1 and 2 position. In heat exchanger, use SFEE 1 to 2. Okay. So H1 plus 1 by 2000 C1 square plus GZ1 by 1000 plus heat is equal to H2 plus C2 square by 2000 plus GZ2 by 1000 plus work. We know that it's at same head, 1 and 2 position are at same head from the datum. So this is 0. Then velocity is remaining same. C1 and C2 both are same. So kinetic energy is also 0. Temperature is there, definitely. And heat exchange they have asked, rate of heat transfer. So a heat exchanger doesn't give us any work. So this is also 0. So you are left with the equation, that is H1 plus Q is equal to H2. So Q is equal to H2 minus H1. And they have asked, what they've asked? Heat transfer. So in terms of kilowatt you need to give. Okay. So if it in terms of kilowatt, then it will be M dot H2 minus H1. Okay. Mass flow rate will also incorporate here. Right. Oh. All right. I won't write. I will write like this only. So heat transfer is MS3 CP T2 minus CP T1. Okay. Air is treated as an ideal gas only. Okay. 3 into what is CP of air? In the first tutorial we did 1.005 kilojoule per kg Kelvin. 1.005 T2 minus T1, that is 850 minus 15. So it's a difference. That's why we are not converting it from degree Celsius to Kelvin. Difference always, even if you write 850 plus 273 minus 15 plus 273. So 273 is eventually going to cancel out. Okay. So I'm just writing 850 minus 15 degrees Celsius. Okay. Now you need to solve it. 850 minus 15 is 835 into 3 into 1.005. So that gives you roughly 2517 point, or you can say 272518 eventually kilowatt. Okay. Earlier it was kilojoule per kg, but it's a mass flow rate is also there. So kilowatt, the second equation which we have used of SFE. So first part we got our answer. That is the heat flow, heat transfer in the heat exchanger. Now let's come to the next part. Power output from the turbine, assuming no heat loss. So state 2 to 3. Power output they have asked, basically work output they are asking. Okay. So again use SFE in turbine. Use SFEE from 2 to state 3. Okay. Again H1 into 1 by 2000 C1 square plus GZ1 by 1000 plus heat is equal to H2 plus C2 square by 2000 plus GZ2 plus by 1000 plus work. Okay. So they have said power output they have asked. So first of all, temperature is definitely different. So H1 and H2 are not going to cancel anyway. Then speed is also different this time. So that's also not going to cancel. Potential head is going to cancel because it's at the turbine is at same head and heat interaction is not there in the turbine. Okay. So we will cancel out this heat interaction and so this. Okay. So we are left with H1 plus C1 square by 2000 is equal to H2 plus C2 square by 2000 plus work. We want to have work output, and it's a rate. So I'll multiply the equation with mass flow rate as well. So that will be H1 minus H2 plus C1 square minus C2 square by 2000. Okay. I'll just rearrange the terms. What is M3 Cp T1 minus T2. So 1.005. What is T1? Sorry, T2 minus T3. We are dealing in the terms of 2 and 3. So what is T2? 850 and T3 is 600. So why I'm writing 1, 2 here? My bad. I'll remove every of subscripts from 1, 2. Okay, right? Again, H2, C2, GZ2, H2, C2, GZ2, Z3, sorry. H3, C3, GZ3. So it is C2 square, C3 square. Is it H2, C3? And this is H2 minus H3, C2 square minus C3 square. Okay? Like that. All right. So what is H2 minus H3? T2 minus T3 is 850 minus 600. 850 minus 600 plus what is C2? 35 and C3 is 65. So 35 square minus 65 square by 2000. Let's solve it. So 35 square minus 65 square divided by 2000 is negative of 1.5. So this is minus 1.5, and 850 minus 600 into 1.005. So that is 251.25 into 3. So minus 1.5 into 3, that is approximately 749.25. 749.25 kilowatt of power output you have produced from this. Okay, so you see how much you heat supplied in the heat exchanger and what you have received in the work output. It's almost less than 1/3. So that will come into the second law of thermodynamics. We will deal with all these things, the efficiencies and everything. Okay. All right, we have got coming to the next part, velocity at exit from the nozzle. Third, you can re-verify the answers as well. Okay, and solving in front of you only. Next part, they have asked velocity at exit from the nozzle. So from nozzle is 3 to 4. So C4 we don't know, we know the C3. So in nozzle, using SFE from state 3 to state 4. Okay, so that is S3 plus C3 square by 2000 plus GZ3 by 1000 plus heat H4 plus C4 square by 2000 plus GZ4 by 1000 plus work. We have asked velocity. So again, nozzle, there is an increase in the velocity, but at the inlet velocity is not zero. We assumed in defining the nozzle that velocity at inlet is much or velocity at outlet is much higher than velocity at inlet. So we can neglect the velocity at inlet. But here velocities are there, so we cannot neglect. But datum head we can neglect. There is no heat interaction in the nozzle. There is no output from the nozzle. So we are left with S3 plus C3 square by 2000 is equal to H4 plus C4 square by 2000. Put the values. C4 square minus C3 on rearranging, you will get S3 minus H4. Okay. So what is H3 minus H4? CP T3 minus T4 into 2000 and C4 square. What is C3 value? 65. 65 square. All right. So what is T3 and T4? T3 is 600 and T4 is 450. 1.005. 600 minus 450 into 2000. So 600 minus 450 into 2000 into 1.005 plus 65 square under root of that. C4 comes out to be 552 meters per second almost. Okay. So quite a high velocity we have achieved after passing the fluid through the nozzle. Okay. 552.9. So we can write 553 here. Just a second. Okay, I think this question is understood by everyone. Any doubts? No doubts? We have a new question where we have a chamber, insulated chamber. It is separated. So the left side has the properties P1, V1, T1, and right side has the property V2, V2, T2. Okay, whatever gas is there. Now this membrane is open and both mix up. It's not a free expansion because there is no vacuum. Okay, we can't say it's a free expansion. There is a resistance. So final pressure is P3, V3 volume, and T3 is the temperature. When you need to get the expression for final pressure and final temperature. Fine. P3 and T3. Let us do. Pretty simple. Take a minute, think how you will do. Okay, so we'll consider that this is a free expansion. My mistake. We'll consider that this is a free expansion. Though vacuum is not there, but expansion is happening in a free expansion way. Okay. Let me rectify. It's a free expansion. Now you will do. Thanks for pointing out in the chat. All right, pretty easy. So as it's a free expansion, so you can say that initial, final and initial internal energies are same. Okay. What is final internal energy? U3, and initial internal energy is U1 plus U2. Okay. So these are internal energies. Since you know that internal energy is U by M. Oh, sorry, M into U. So my bad. Or you can say specific internal energy is U by M. So U will be M into U. So this is M3U3 is equal to M1U1 plus M2U2. All these are specific internal energies now. So we know that M3CV T3, it's an ideal gas here, M1CV T1 plus M2CV T2. Okay, so mass is same. Mass is gonna be conserved. Yeah, so MCV is same, but it cannot cancel out. So M1, M2, mass is conserved means M3 is equal to M1 plus M2. Okay, but not all the values are same. Understand this point. Okay, but what we can do from the ideal gas, you know that MRT is equal to PV from the ideal gas law. So we can write M into T as PV by R. Okay, R is a gas constant. All right. So this can be written as CV. CV is gonna cancel out because it's the same. CV cancel out. So M3 T3 is nothing but P3 into V3 by R. P3 V3 by R is equal to P1 V1 by R, P2 V2 by R. Okay, this R is also gonna cancel out. So P3 is nothing but P1 V1 plus P2 V2 by V3, and V3 is nothing but sum of V1 plus V2. That is V1 plus V2. Since final volume is sum of initial volumes. Alright, you got the pressure expressions. You got the pressure expression, that is P3. Now use the mass conservation. From mass conservation, because in this pressure you have all the values. P1 is given, V1 is given, V2 is given, V2 is given. Okay. Your M3 is M1 plus M2. From the ideal gas law, PV is equal to MRT. So PV by RT is M. So P3 V3 by RT3 is equal to P1 V1 by RT1 plus P2 V2 by RT2. So R cancels out. Okay. So what is T3? You have to get out of it. The T3 is P3 V3 by P1 V1 by T1 plus P2 V2 by T2. Okay. Just rearrange. Take this on the right hand side and take this on the left denominator. So that is what I have written. All right, this is your T3. You have all the values P3, V3, P1, V1, T1, V2, V2, because P3 you have got from above. All right, so this is the temperature value. Now we are done with steady flow energy equations. Now let's come to unsteady flow energy equation. The concept of unsteady flow energy equation. So from the word unsteady means that it is dependent on time this time. Okay. So unsteady flow means properties are varying with respect to time this. Okay. So mass at entry and exit of the system of the control volume are different this time. And unsteady problems are solved by using two conservation principles. One is mass conservation, second is energy conservation. Let me write all these points. Unsteady flow means property are varying with respect to time. Therefore, mass at entry and exit of the system or control volume are different, and steady state problems are solved by using two conservation principles. That is mass conservation and energy conservation. All right. So again, we'll define a nomenclature here. So we'll say that MI. MI is nothing but mass at inlet of the control volume. So I'll write control volume as CV. Then mass ME is nothing but mass at exit of control volume. All right. Then mass M1 is also there. What is that? Mass, initial mass inside the control volume. So control volume itself has some mass inside it. Initial mass inside control volume. And M2 is will be also there. Final mass inside control volume. Right? And M2 will be greater than M1 only because if you say that some flow is happening from to the inlet and initially there was mass, so some mass will accumulate inside the control volume which will increase the mass. Okay. All right, so we'll make a diagram for this again of the control volume. And we'll define a datum here. So again, this datum has flow has inlet, it has outlet. This is your control volume, which has mass, initial mass, and right, initial mass M1. It's a control volume, and final mass M2. Okay, in the control volume. This is your control surface. We have discussed all this. Okay, and the head, initial head is at Z1. The head here is at Z2 of the outlet. Okay. Then mass is in the inlet is Mi and mass at exit is Me. Okay. Me. Rest all the properties are same, H1, U1, T1. That will be remaining the same. I'm not writing it again. Now, first conservation law is apply mass conservation. So from mass conservation, the rate of change of mass from mass conservation, the rate of change of mass conservation. So mass conservation says that rate of change of mass is equal to rate of change of mass at inlet minus rate of change of mass at exit is equal to dmi by dt minus dme by dt. That is nothing but mi dot for the rate minus me dot. Okay, this is your mass conservation. That means properties are varying with respect to time here. That's why it's a differential with respect to time. Next is the energy conservation. Next law is energy conservation. It states that dE, the total energy with respect to time, is nothing but d by dt of all the properties, all the energies, all the heat heads, everything at the inlet minus at that to the outlet. So d by dt of mi h1 plus potential energy at 1 plus kinetic energy at 1 plus heat. Okay, minus, right on the separate line, minus d by dt of mass at exit h2 plus potential energy at 2 plus kinetic energy at 2 plus work. So this is state 1, this is state 2. Okay, 1 and 2 are the subscripts used. So here mass is being multiplied itself at the entry and exit because we are doing a mass balance. Okay, masses are not same at inlet and outlet, unlike in the steady flow energy equation. This is an unsteady flow energy equation. Okay, now we'll do some assumptions here. Let's take some assumptions. Assumptions will take that, will neglect the kinetic energy changes, will neglect the potential energy changes. Neglect kinetic energy and potential energy changes. Okay, and neglecting the variation of enthalpy at inlet and outlet with respect to time. This is also assumption we are taking. Neglect variation of enthalpy, that is dH by dt. We will neglect. You will get to know that how this expression comes. Variation of enthalpy at inlet and outlet with respect to time. Okay, so dE by dt, because E is sum of kinetic energy, potential energy, internal energy, d of dt of kinetic energy plus potential energy plus internal energy. Okay, microscopic and macroscopic form, which we have discussed in our previous tutorial. So this is 0, this is 0. So dE by dt can only be written as du by dt, change of internal energy. Now put this du by dt on the left hand side of the equation, of the energy equation, energy conservation equation. So du by dt and the right hand side will look like d by dt of mi hi plus q, because kinetic and potential energy heads are neglected in the assumption, minus d by dt of me plus work. Okay, very important equation. Now we'll take the differentiation also in this. Let's differentiate. Let me first highlight this equation. On differentiating the right hand side, so du by dt differentiate the first term, d by dt of mi hi. Mi hi. Okay. All right. So I'll do one thing. Instead of 1 and 2, I'll write hi, e and I, so that there is no confusion. This is state I, this is state E. Okay. So here it will be hi, pi, ki, and instead of 2, it will be e, he, potential energy and kinetic energy. Okay. No confusion. Nomenclature is same now. Okay. D by dt of mi hi plus dq by dt minus d by dt of MEHE minus dW by dt. Now, if you see, the variation of enthalpy will come. First, by the chain rule, you are going to differentiate. So first thing is Mi d of Hi by dt plus Hi d of Mi by dt. So we have assumed that this will be 0. Okay, change of enthalpy will be 0. Similarly here, d by dt. Oh, first Me d by dt of He minus He d by dt of Me minus dW by dt. Again, this variation is also 0 at inlet and outlet. We have assumed this thing. So final expressions comes out to be du by dt is equal to Mi dot. So for this, I'm writing Mi dot Hi plus Q dot. Oh, I have missed the term Q here. I've missed the term. So what I'll do is place something here. Plus dq by dt was also there. So dq by dt I'm writing as Q dot minus Me dot He minus W dot. Okay. So although you can write like this as well. Okay, in this term. The final expression of unsteady flow energy equation in terms of internal energy comes out like this. The application of unsteady flows, you can say that charging or discharging of tanks or bottle filling processes are some unsteady flow equations are used very easily here. Okay, and if the enthalpy variation is not given with respect to time, then you can neglect that also. Okay? That's an assumption which we have taken. All right, so I'll write this was from my end. We are done with the 2 hours of session of the tutorial from 6 to 8 p.m. today. So in the next session, we'll start with second law of thermodynamics. And I hope that you all are regular to your lecture videos, to the assignments on the Nptel portal given by the professors, as well as if you have missed any of my tutorials, you can watch the tutorial on the recorded. These all sessions are recorded and uploaded on the YouTube. So you get the Excel sheet on your email. Those who are registered, they can see the sheet and where the link of each tutorial, recorded tutorial, as well as this PDF will be uploaded on the Google Drive. If you are you are watching this video first time on the YouTube, not enrolled in the NPTEL course, then you can go into the group description and you'll get the PDF of all the week tutorials. Okay, so my YouTube channel is, I'll write here, NPTEL with Varnit. Okay, with NPTEL with Varnit. So this is my channel. In the group description, you can see all the PDFs. Okay, I hope there are no doubts. Any doubts to anyone? Or we can end the session. All right, if there are no doubts. So